Right. So yeah, so welcome once again to this session, live interaction session. So yeah, please go ahead, and Nikita, you had some questions about the single object allocation, right? And you want an example how this works.
Yes, sir. Yeah. Because I went through the video for single object allocation and that had the explanation for the subgradients and the properties for
Okay.
convex. Yeah. So.
Okay, so you want the topic which is related to the essentially the optimal option, right? So
Yes,
single
sir.
object allocation, but our objective is to maximize the revenue.
Yes, sir. Exactly.
So let me, so maybe let me share my screen, the easiest. So so it is module 55 onwards.
Yes.
The screen is visible, right?
Yes, sir, it is.
Okay. Okay, so here, but yeah, so let's follow the notation that has been used here. So every agent now has an interval, sort of a subset of this real line, and that is where its type is. So its value can lie anywhere within this interval Ti. And now the allocation rule, as before, is so every agent's type is now just a number which falls in this interval. So, for instance, if the type, so let me just. So I think my writing is visible now, right? So this is the type set for their I. So you can imagine as an example, let's say this this Ti is an interval between, let's say, 0.1 to 0.5 or something, and a specific type which we denote by small lowercase Ti can be some number inside it. Now the setup that it discusses, so suppose every agent picks one type. So my mouse pointer is also visible, right?
Yes, sir, it is.
Okay. So once all these agents pick their own types, the allocation rule essentially allocates this item in a randomized fashion, right? So each of these agents have some probability of winning that object. So there is only one object. So among this set of agents, we are just picking someone who will get that object, right? So therefore, this set of allocations is given by this set A, the delta of A, which is nothing but an allocation which lives in this space. So 0 to, so it's a vector of numbers which are between 0 and 1, and collectively they all become, so if you take the sum, then it becomes 1. So that means if A, say let's say A2 is equal to 0.2, so that means that player 2 has 20% chance of winning this object. So that is the outcome of this. So this is typically what is called the randomized mechanism or randomized auction. So where we are trying to give the object not in a deterministic way, rather in a randomized randomized. So if a specific, so what will be the if you say the expected valuation of an agent? This is just the probability that it wins the object and multiplied by the value that he has for that object. So AI times Ti is the value for that agent under this allocation A. We just follow. All right. So as before, so if you can consider this F, it is a member in this delta of A, right? So F of T finally, when you take this, so go back again. So if you collect together all this T1, T2, up to Tn. These are the types that has been reported by these different agents, and you apply f on that. So what you essentially get is a vector. Let's say that vector is a1, a2, up to an. And each of these numbers, so ai, so each of these ai lives between 0 and 1, with the additional condition that if you take the sum of all these agents or all these ais, that will be exactly equal to 1, right, from 1 to n. So that is why we can denote. So this function essentially is a vector. So we can denote the ith component of it. Sorry. Yeah, can you please mute yourself if you're not asking any question? Yeah, okay. Or was there any question? Okay. So if I of t essentially denotes what is the probability. So this says the probability of agent I winning that object. Winning the object or winning the auction. So quite naturally, if you take the sum over all i's of FIT, that will definitely be equal to 1. Okay, so this is the setting. This is the premise that we are working in. Now we have discussed the second price option. So this is, you can think of this as a special case of a second price option. So second price option is a special case of the description that we have just given. So here, if you define the second highest valuation for that agent, for everybody except that agent, and define that with t minus I2. So that means in the space where you have agent, if you have removed agent I, what is the highest value among the agents except agent I? So that we are going to define as t minus I2. So how can you define the second price option in this way? That agent I will win if its own valuation is larger than or maybe equal to this. So you can break the ties in any way if there is an equality. And if it loses if it's not the highest. So what this means is that agent I's valuation is the highest. It beats even the maximum of all the other agents' valuations. So that is one specific way how you can define this second price option. So if you look at utilities, in terms of utilities, then it is going to be 0 if it is less than or equal to 2 minus I. And oh, okay. So this is the second price option. So we'll also have to define what is the payment of this agent. So its payment will be the second highest bid. So if it wins, so for instance, in this case, if the player I wins, then it will pay this amount. So for all the cases where it is exactly equal to t minus I2, or it is smaller, if it is smaller, it loses the object, so its utility will be 0. And if it is equal, then also it pays the second highest bid, which is also, which the difference of which will also be equal to C. So essentially, the final outcome will be VI, right? VI minus t minus I, so which is going to be 0 in all these cases. Only if it is strictly greater, it is going to be something positive, and that is going to be its utility. So what we observe here in this second price option is whenever this agent wins, how does its utility look like? And this is not just a coincidence. I think that's the point that I was trying to make, is that as long as your evaluation is below this second highest bid, the utility is going to be 0, and after that it monotonically increases with the slope of 1. So I believe everybody is familiar with the convex function. So convex function, let me just go back again. So a convex function for there is a formal definition, but what I can tell you is that if you take any function, so let's say this is the shape of the function. How can we test that it is a convex function? You take any two arbitrary points on this function, and if you join a line connecting these 2 points, every point in that line will lie above this curve. So that is what is called a convex function. You can define it in some different way. So for instance, if you have this point to be x and this point is y, and you take any value which is lambda times f of x plus 1 minus lambda times f of y, which is essentially nothing but so these lambdas are always between 0 and 1. So you are essentially picking some point here. That is going to be at least as much as the actual function value at that point. So f of lambda x plus 1 minus lambda times. Was there any question? Jan? Otherwise, you can keep your mouth muted. I mean, your speaker, microphone muted. Okay, so this is the convex function. So what we actually see is whenever we are looking at this kind of a function, the utility of this agent for every agent, this is going to be a convex function as a so convex in terms of its valuation, its own valuation. Why? Because if you look at this function here, for all the cases where valuation is less than t minus I2, a specific value, it is going to be 0. And after that, if you increase bi, it increases in a linear way and with a slope of 1. So that's the thing. And if you look at the corresponding allocation, you see that it's just a derivative of the corresponding utility. And that is exactly what we have discussed in the video lectures. So of course, you cannot define that derivative at this point because it is undefined. The derivative does not exist. But for that, we have this idea of subgradient. Now, I think that is essentially the question: that what is the subgradient? So let's come back to this definition of subgradient. So for any point x in the domain of this function, let's say g, your x star. So you can define a function. So essentially, the idea is the following. So let's go back. Yeah. So this picture essentially shows it. So this function is not differentiable at this point x. So we can still write a kind of because this function is a convex function, we can still draw a kind of a supporting line where the entire function will lie above that line. So suppose, and that line is not unique. So as we have drawn, so if you draw it, so let me go back again to the working. So let's say go to the next page. So suppose we take that function, and this is a specific subgradient. This can be one subgradient, but similarly there can be another subgradient which is slightly different. So both of these, let's say this is x star and this is y star. Both of these things are x star prime, just to make it x star prime. So both of these things are subgradients. Why is that a subgradient? Because if you write the corresponding function, so let's say let's go back to the definition again. So the point is that we are trying to write is gz should be at least as much as g of x. So you pick any arbitrary point x, and you take this the difference from that that point z minus x and multiply with that x star. So what should that mean in this context? Let's go back again. So it means that if I pick any arbitrary point, let's say, yeah, so I want to define subgradient at this point x, and I am picking any arbitrary z here. So I want to find the value of this function here, so gz. So what should happen is that if I take a slope from this point with this x star, and then take this difference. So z minus x is essentially this difference, and your x star is essentially the slope at this point. So therefore, you actually get yeah. So this point here. So this particular point. So if you check carefully, this right hand side is essentially this point here, where okay. So if I draw it a little more in a slanted way, then I think it should be a little more clear. So let's say this is my x star. So it's slightly above this point here, which is x. So you are taking this x star times z of x, z minus x, which is actually giving you this much amount of height. So this height is essentially this part here. And then you are adding that to this gx value. So you are getting this point. The point is that this gz should always be lying above this point here. And if it is not true, then x star is not a subgradient. And now you can verify that for every z. So no matter wherever your z is, you can see that that point, the corresponding point on this line, will always be above, or will always be below the function here. And you can look it from the other side. So z, if z is on the other side, that means z minus x is negative. So that means you are falling below. Then certainly g of z will actually be above this. So this is how we can define a subgradient as something very similar to a gradient, where I know that the function is not differentiable. So one quick check is for those points where and the derivative exists. So for instance, if your x was here, then there was unique subgradient, which is the gradient of that function, right? So this is one interesting thing about convex functions, because you can always keep the function above a specific line. You can in those points where the function is not differentiable, you can define something like a subgradient. Okay, so why is subgradient important in our discussion? And that is exactly where we come in. So our objective is to show. So if you look at this part, so go back to this original example. So you see that this utility function is a convex function, but it does not have any derivative here. So the derivative does not exist. So okay, so we can, with this notion that we defined just now, we can define a subgradient. Right? So subgradient will be any number between, so the slope of this point can be any point between 0 and 1. So you see that when you look at the allocation space, you can accordingly choose any number between 0 and 1 and call that as the allocation for agent I. So let's say this is agent I, and you are defining any number between 0 and 1. So which means that what is the probability with which this agent will be winning this auction? That can be any number between 0 and sorry, between 0 and 1. So that is essentially the idea of this subgradient. Okay. Okay, so that is essentially the definition of subgradient, I think. So then we have actually stated a few results, which is actually coming directly from convex analysis. So do you have any specific questions for those results, or?
No, sir. No, sir. Those were, yeah, those are completely fine.
Okay.
Yeah.
All right. So yeah, so the overall idea is that so we can define this idea of subgradient when we have a convex function, essentially sort of a supporting line which supports this the function, and that line is going to be unique for a point where the derivative exists, and the places where the derivative does not exist, that subgradient will be non-unique. Yet, what we show later is that all of those things, all of those subgradients, is a valid allocation for that utility function. Okay, so Okay, so please ask any other questions which might be of related nature.
So if the others don't have any questions
Yeah.
related to this, then I had so it's a really small doubt, but it's the last question of the assignment and the last module, the
Okay.
example given in module 58, sir.
Okay.
That was with respect to like the BIC. So
Okay.
so I had a doubt in the matrix, for example, where it was non-decreasing expectation and it was non-decreasing. So
okay. Okay, so let me just
yes, sir.
go
So the
back.
non-decreasing expectation part was fairly clear. So that was completely understandable. It's just that the non-decreasing, so to quote the notes which are associated with the course,
Okay.
sir, the last paragraph of this particular section says, hence the allocation of agent 1 is NDE. Understandable.
So which module this is, so that I can also, for
So
consistency,
it's
I can also
module 58.
58. Okay. Now you can
Yeah.
see. Okay.
And this is so the figure where the ones represent the object allocation to agent 1 and the blanks represent the object allocation to agent 2.
Okay, just
so yeah.
Yeah, this example here, right?
Yes, sir. Yes, sir. Exactly this.
Okay.
Yeah. So my doubt was that after this what we say is that the just a minute, I'll open it up on my screen as well. Yeah, it says that the allocation of agent 1 is NDE. So which was completely understandable, because if we end up making that distribution table, then we can see that it's NDE. So however, the last part of this was that the allocation is not non-decreasing.
Yes.
Since T2 belonging to 1 by 5 to 2 by 5, since in T2 belonging for 1 by 5 to 2 by 5, agent 1's allocation decreases from 1 to 0.
Right.
So that specific part, I don't know why, but it's just, for some reason, I cannot like get that settled in my mind.
Oh, okay. So let's discuss this. I think this is a good example. Okay, so your pi IT. So let me just figure out how pi IT was defined. So yeah, so the allocation is certainly and talking about the expectation, right? So it is talking about this. It is non-decreasing in expectation when you are taking the expectation with respect to the type of the other groups.
Yes, sir.
So let's say I look at, so this means that in these places, agent 1 is the winner. So T1. So that is the type of player 1. So player 1 has 5 types. Let's call them T1, 1, T1, 2, and up to T1, 5. Similarly, T2, 1, T2, 5. Let me just redraw this example in my Jamboard so that I can explain it well. It's slide. So okay, so the numbers of one. Okay. So this is, I'm just replicating the example to discuss. So D1, right? So there are 5 possible types for player 1. And similarly, player 2 also has 5 possible types. 2, 3, 4, and 5. So what does NDE say? And assuming that all these T1s and T2s are equally likely, right? So it is assumed that it is uniformly distributed. All these T1s T1 can take any of these 5 values with equal probability, which is 1 by 5. Similarly, T2 can take any of these 5 values with probability 1 by 5. So non-decreasing in expectation would say that if you're, let's say you are player 1 and you're talking about T1, I forgot what was the notation used there. So I think just T1 means that when your type is, let's say T1, what is the expected probability of getting allocated to this agent? Essentially, you are taking the expectation with respect to the other players' types, right? So let me just, yeah, so this is the way. So the probability that you are so what is the distribution over all this S minus i's, which in this case is independent, so 1 by 5 for all of them, and then you are taking the expectation with respect to your so this is the payment part. So we should be looking at the allocation part. So I have used a wrong notation. So here it is the probabilistic allocation for this agent. So in this case, this if I SIS minus I is already well defined, right? So if we go back here, so it should not be I, it's not notation. So it is alpha 1, right? So what does alpha 1 mean? So here your F11, so let's say F1 of let's say T11, T21, right? So I'm looking at this specific cell here. So this, what is this F1, T11, T12, T21? Can you tell me what that value is? So when player 1's type is T11, so this is this first one.
The object is allocated to T2.
Yeah, so the object is allocated to T2. That means F1 will be
0.
It will be 0. So yeah, so this is 0. Similarly, T12, T21 is also 0.
Yeah.
But F1 of T13, T
1 by 5.
Yeah, so this is this is 1. So this is the deterministic allocation part.
Okay, okay.
So we will do this expectation after we look at it. So for instance, let's focus on player 1 only, and suppose its type is T11, right? And we have seen T12 is 0. Actually, if you look at it, T22. So I'm looking at, let's say, the next cell. So I'm looking at this cell, right? So this cell, what will be the corresponding F1T1, FT11, T2?
Again 0.
Again 0. So essentially, you can look at all these points here. So essentially, everything will be 0 up to. So I'm not writing the intermediate steps. T25 up to everything will be 0. Now using that formula, you can calculate what alpha 1 T1 is, right? So all this, every entry here, because you are running over the other agents types, right? You are running over all the other agents types. So in this case, T21, T22 up to T25 are all those cases in S minus I. So for all of those cases, it's 0. So finally, alpha I of let's say T1 in this case. So let's say alpha 1 T11. So alpha 1 T11. Which is nothing but, in this case, it will be a summation because these are all discrete. So you are taking this F1 of T11 and T21 and multiply that with the probability of that. So yeah, so the probability of G minus, so that is G2 of T21 doesn't matter. This number is 0. So therefore, if you take the summation F2 T1 T22 and similarly G2 T22 and so on. So you'll have 5 such numbers here. Calculate this value, but each of these is 0. So therefore, this is going to be 0. So what do we get? So if I look at only player 1 and assume that the player 1's type was T11, that number is going to be 0, right? Is that part clear?
Yes, sir, it's clear.
So now, what about alpha 1, T12? Okay. So we are now focusing on the second entry. If you do the same exercise, see that everywhere player 1 does not get the object. So what will be the value of it? So you can, yeah, so all that will change in all these cases is that.
Yes, sir. It will again become 0 for all of them.
Right. So again, it will become 0 because it's 2 to replace everywhere. You get that this allocation is also 0 for player 1. So yeah, so this also becomes 0. But when I come to T13, I see that at least for the first case. So when I have this case here, so when we look at this 3, so I know that in these other cases, so when the agent 2's type are T22 and above, then this numbers become 0. So all the later ones, the coefficients later will be 0, but this one is 1. And that is getting multiplied with 1 by 5, which is the probability with which player 2 chooses this first allocation, right? So first type. So therefore, at this point, it will be 1 by 5. This is how we get it. And similarly, alpha 1. So now I think you are getting this idea, right? So how, so once we have this kind, so here also we saw that everywhere it is, it was 0, but here only in this part it was 0. So we got the kind of contribution from this part, which is 1 by 5. So in the next type, so for T14, so when we go there, T14, let's say, what should be this value of alpha 1 T14?
2 by 5.
It will be 2 by 5. And finally, alpha 1 T15
will also be, that will
no,
be 3
it
by
will be
5.
3 by 5 because there are 3 ones now.
Yeah.
Now, this is, so when we are saying that this number is monotonically increasing or at least non-decreasing, we say that it is monotonic, non-decreasing in expectation because you are taking the expectation with respect to the type of the other players. So here there was only one other player. So player 2, so when we are looking at what is the expected allocation of this object to player 1, when its type is, let's say, T11, it is 0 because you have already expected over. So this this number is essentially expectation, taken expectation with respect to the types of the other players. That's what we have done. But if you, so remember the definition of non-decreasingness. So what is non-decreasingness? There we look at the original allocation itself, right? This F1, T1, T2, and see if this number is increasing or non-decreasing for every type T1. Every type T1 and for every type of the other. So if you recall this definition of non-decreasingness, let me go to the next slide. So the non-decreasingness says that if, let's say, I of Ti, comma T minus I should be non-decreasing in Ti for all. So for all T minus I's, right? So no matter what the other players are doing, other players types, choices of types are, we are not taking any expectation. We are saying that for that choice of T minus I, this should be monotonically increasing in Ti. Right? So this is one way of writing it. So it's monotonically increasing in Ti for all T minus. Now let's come back to the previous example. Does it hold? So for instance, if I look at the type of the other player, so let's say player 2, its type is T21, right? Now I know that if f of, let me erase up a little bit. So this part is 0, I know. Yeah. So this part is okay. So this part is 0, I know, and similarly F1, T1, 2, T2, 1, sorry, T2, 2, sorry, no. So I'm holding the player 2's type to be T2, 1, right? So I'm focusing only on this type of the other player. This is also 0. If T 1, 3, comma T2, 1. This is 1, so still no problem with the monotone non-decreasingness. But here is the problem. Now I increase FT1 to T1, 4 and T2, 1. What is this? What is the value of this? And player 1's type is, this is 0. So we see that there is a violation. So yeah, the allocation function was 0 up to this T1, 2 point, and then it increased to 1, and then it fell again. So this violates the monotonicity condition. So therefore, this function, this allocation function, is not monotone non-decreasing, but it is non-decreasing in expectation. When we take the expected value, so it is non-decreasing. But when we fix a specific type, and you can see this in multiple other places. Here also, you increase. So these were 0, this is 1, and then it falls to 0 again. Right. So, and yes, for player 2 also, if you want to look at in this way, you see that here agent 2 was getting allocated. So its allocation. So F2 was 1 in this case, but then it fell to 0 because player 1 getting this means player 2 gets the probability 0. So its allocation function also goes down. So it violates the monotone non-decreasingness.
And so do we check the allocation for both of the agents? So for example, if I'm getting non-decreasing.
Oh, no. So I mean, violation for any player is enough. So
yes, no. So I'm saying that if for agent 1 we're getting it's non-decreasing in expectation and non-decreasing in terms of its monotonicity, do I end up checking for agent 2 as well, or do I just stop there after checking for agent 1?
Right. So if you it depends on what you are going to claim. So if you are saying that this function is not non-decreasing, then it's sufficient, or non-decreasing in expectation. It's sufficient to just check for one player, because look at the definition. So the definition says that it is non-decreasing in expectation. The definition of non-decreasing in expectation. It is non-decreasing in expectation is for all players I, and for all SI TI such that SI is greater than less than TI, you have this. So to negate this, you need just one agent who violates this condition. So as soon as you find one player whose this condition is getting violated, you can conclude that it is not non-decreasing in expectation or not non-decreasing. You don't really need to check all players.
Okay, sir. Okay. Yes, sir. So I've understood.
So maybe you can create some more examples like this. So essentially, yeah. So this is a nice example where, so what essentially we did was that if you have uniform thing and you just put this 1 at some point, right? So at any place. So it's not necessary that 1 will be here. 1 could have been here as well. And there also you do not violate the condition of non-decreasing expectation. Actually, okay, so maybe for player 2 you violate it. For player 1 you don't. But for player 2 you will have.
Yes, sir. That was why I was asking, because player 2 there's a violation that's 2 by 5, 2 by 5, 1 by 5. Yeah.
Right. Yeah. So because there what will happen, it will so for player 2 the allocation initially will be 4 by 5 and then it will go down to 3 by 5. Right. So for player 2, if 1 moves here.
Sorry, yeah, I was looking at the opposite. Yeah.
Yeah. So if
2
1
by 5,
moves
3
here,
by 5, 4.
Yeah. So then, yeah. So player 2's expected allocation was 4 by 5 initially, and then it goes down to 3 by 5. So that's not a valid example. This is certainly a valid example. Yeah, but there are many such ways you can create such a matrix which is non-decreasing in expectation but not non-decreasing.
Got it, sir.
Okay, so any other questions? I mean, yeah, so other participants are pretty quiet.
Sir, can you explain the numeric example in charts?
So the numerical example in which? Oh, okay,
Posted in
in the chat. Okay. Apply BCG payment rule and find the utility of layers P1, P2, P3. Okay. Yeah, so what does it say? Outcome one. So yeah, so I don't immediately recall the question. So I think the question is that if outcome one is chosen, player one gets an utility of 105, player two gets 80, and player three gets 110, right? That's what the meaning is. So the question, okay, so for stay on the same page for everyone, let's write it down. Okay, so the question is that yeah, that's a lot of text. So I think, yeah, so what you wrote is correct. So P1, so player one, player two, and player three. And there are two outcomes, outcome one and outcome two. And the values are 105, 80, 110, and 150, 150, and 90. So the interpretation is that yeah, if outcome one is chosen, so this outcome is chosen, then these players get these utilities, right? And if outcome two is chosen, these players get this utilities or values, right? Yeah, am I correct?
Yes, sir.
Okay. Okay. So yeah, so you can, I mean, as a running example, you can think of this as a choice of, let's say, a park versus a museum, and different people can have different happiness if one of those things are chosen, one of those outcomes are chosen. Okay, so you haven't shared my screen, so nobody told me about this. Okay, so this is what I was drawing. So now the screen is visible, right? Okay, so now first thing, what we need to find out when we do the BCG mechanism is to find the allocation. And how do we decide the allocation? For BCG. Yeah, can you tell me what is the allocation rule for BCG?
Get the maximize profit, sir.
Not maximizing the profit, maximizing the sum of the values, right? So for instance, if I pick O1, so what is the sum of the values? So what is the sum of VIs on O1? Okay? So which means you are looking at the sum of this row, of the first row. Right? So 105 plus 80 is 110, which makes it 595 to 95, right? If I'm not mistaken. And similarly, what is the sum of the valuations when the outcome is O2? Can someone do the calculation for me?
$300.
300 and 370. So which one of these outcomes should the mechanism? So in the VCG mechanism, which one of these outcomes should be chosen? Hmm?
So just we have to take out the payments for P1, P2, and P3.
Yeah,
So
that is the second
allocation,
part. That
yeah.
is the second part. Let's first solve the allocation part. So which allocation will be chosen? Which of these two? So let's say the first one is a museum, and the second one is a
376.
yeah. So let's say museum, and the second one is a bridge or pond, whatever. So which one should be picked?
The bridge.
The bridge. That is outcome 2. So this will be the choice. Okay, so now A star, that is the allocation in VCG, is turns out to be O2. Now that this is O2, now we'll have to calculate what are the payments for each of these players. And in order to find these payments, so what do we actually apply? We apply the following rule. So when we are, let's say, trying to find the valuation or the payment for player 1, we just remove this player 1, right, from the system, and see what was the outcome. What would have been the outcome in a very similar way. So look at the same allocation rule, as the VCG. If player 1 was not present, then what would have been the outcome? So you can see that here it will get 190 as the sum of the values, but here it is 220, right? So you see that outcome O2 remains the same, right? For player, yeah. So if player 1 is removed, if P1 is removed, the outcome is still O2, because this is higher than this one, right? So in some sense, player 1 is not a pivotal player. That is one way of interpreting. So player 1 should pay. So let's say if we denote that with pi of player 1 is going to be 0. Because if you remove that agent and you look at the sum of the valuations of the other agents, it does not change. So the payment, let's say pi of I is nothing but sum over all the valuations of all the other agents when agent I is not present, right? So that was the notation. So j is not equal to I minus, you look at the bj of A star when agent I was present, but you look at the sum of the valuations of all the other agents. So if you want to just put this in that formula, so you know that here the allocation, the outcome is O2. So you are going to look at the V. So for finding player 1's payment, you are going to look at this V1 O2. Sorry, V2 O2 plus V3 O2, because you are not going to include agent 1 here and taking it as a difference from, again, V2 O2, because even after removing agent 1, the outcome did not change. So V3 O2. I don't really need to put the values, it will always be 0. Now let's look at player 2 in that case. So let's say, yeah, this. There's this. I've done this. Yeah. So let's imagine that now player 2 is not present. Right? Player 2 is not present anymore. Then what happens? So can you find out what is the allocation now? So the sum of the values now becomes 215 for 1 and 240 for O2. Is that correct? Do you see this? So what I'm doing is I'm summing these two things. So 105 and 110, right? And also 150 and 90. And checking which one is larger. So turns out again O2 remains to be the highest. So in that case, player 2 will also have a zero payment. So phi 2. So phi 1 was already 0. Phi 2 also happens to be 0 because it is also a non-pivotal agent. Now, what happens to player 3? Is it a pivotal agent? Yeah, so it turns out that it is, even this is also not a pivotal agent. So yeah, so I think the example essentially shows that none of these agents are pivotal agents. So this VCG mechanism will not give charge anybody any payment. That was the answer. I don't recall. I mean, I'm not looking at the solution. So what was the answer given?
The answer was 20
20 for whom?
payments. So
Yeah.
yeah, it was 20, 0, 25. That's actually utility because the final answer was to calculate the utility.
Oh, okay.
Yeah, but
Yeah.
the payment I can give as well. That's 130, 0, 85.
Yeah, so if this were the numbers, I think none of these players are pivotal players because there's already. Sorry?
I have pasted the answer in charts.
You have check. So there's something wrong here. So okay, so did I? Yeah. So what was the final outcome? Yeah, so 295 is fine. Yeah, I mean, did I do any calculation mistake? I mean, I'm not sure about the calculations whether I have done it correctly, but I have told you the steps. But if these are the numbers, then this should be the numbers as well. So where is 240 coming from? You have given me a wrong input data, I'm sure. 150. So okay, let's see. Allocation. Oh, so this is a different a problem description altogether. Okay, so you are saying that these numbers are okay. Okay, so I think yeah. So there was a basic misunderstanding here. Is that if the object? So there are two objects. Yeah. So that you did not tell me. Yeah. When
Yes, I was trying to point that out when I.
Yeah. So when I asked you, I don't remember the problem itself. I don't remember the problem itself, so I don't recall what is essentially happening. So it says that this object one, if it goes to one of these three players, they get this. So these are two different object allocation. I thought this is a public good, and if this was okay, so if this was a public good allocation, that is either you build a museum or you build a bridge, then this is the answer. But what actually the problem is, it says that if object one goes to player one, then it gets a value of 105. So then the problem, the allocations change completely. The allocation is either O1 goes to P1, or how you can distribute this O1 and O2 between these between these three players. And turns out that if you, so what is the most efficient allocation in this case?
O1 goes to P3 and O2 goes to P1. So the maximized sum is
Yeah,
to
so essentially this is the allocation. So this goes to this agent and this goes to this agent, right? And that gives you 240. Right? Sorry, 260 of the sum of the valuations is 260. Right? So you can, so this item, if it is given to player 2, it's less. Here it is larger. So all possible combinations that you can do, like 150. So P1 goes to so O2 goes to P1 and P3 goes to, so O1 goes to P3. That maximizes the sum of the valuations, which is 260. Okay, so that's the first thing. Now, if I want to calculate, so of course P2 gets nothing, so therefore P2's payment should be 0, which is quite obvious. Now, if we'll have to calculate what happens to P1 and P3. So if P1 was not there, then how would these two objects being allocated? So clearly O2 will now go to P2 and P3 will continue to get the same object under O1, right? So in that case, what will happen is you calculate this thing. So P, let's say pi 1, I'm going to calculate. So if I look at sum of the Bj, A minus I star, so minus 1 star in this case, j is not equal to 1, minus sum over Bj, A star, and j is not equal to 1. So that is in the final allocation. So in the original allocation where P1 was getting O2 and P3 was getting O1, what is the sum of the valuation of player 2 and player 3? So player 3 only gets 110. So here I think it will be 110. Minus, if I remove player 1 from the system, then I know that 130, player 2 gets 130 amount of utility and this guy gets 110. So 130 plus 110. Yeah, is 240. So 240 minus 110 is exactly what that answer is. Okay? Whatever that is. So 110. So this is going to be the payment for player 1. So is this clear now? Yeah. So the problem description was different, and of course I was misguided. And now you can calculate the rest of the things. So yes, next time you remove player 2, if you remove player 2, nothing happens. So we don't really care about player 2. So if you remove player 3, then the allocation, I think the allocation will be 150 and 80, that is 230 versus 235. Yeah, so you see that there is an interesting change that is happening, right? So when you remove player 3 from the system, if you give O2 to player 1 and O1 to player 2, you get 230. So 150 plus 80. Okay. But if you give O1 to player 1, you get 105 and 130 here, and that gives you 235. So therefore, this A minus 3. So A minus 3 star allocation is an interesting allocation where, yeah, so whatever I am showing in red is essentially the allocated items. And therefore, you'll have to calculate the corresponding V minus I's accordingly, and you'll find that corresponding values. Okay. Yeah, so it's a little involved, but I think if you just use the formula, you will get the answer. All right, so we have sort of exhausted. So if we need, if you have any doubts, so 29th is the exam. So before that, we can have one more discussion session. Just post on Piazza so that we can schedule another meeting if needed. Okay. Thanks everyone for joining. Yeah.
Thank you so much, sir.